In this video, we're going to cover all the things you need to understand for solving circular functions. We're going to ignore the sketching side of things for now and just focus on all the key techniques that you need to know for solving circular functions. Enjoy! Okay, let's begin. So this video is going to cover all of the circular functions fundamentals, more or less. This is in the context of having already studied circular functions, so we're going to be pretty brief as far as the detail goes. First things first, degrees, radians, and the unit circle. What's going on here? Well, what we have is different methods by which we can represent the angles within a circle, basically. The whole idea stems from this idea of the unit circle, which is a circle that has a radius of 1. And so if we know that the circumference of a circle is 2 pi r, then all we're doing is subbing r equals 1 to get the circumference of 2 pi. So fundamentally what radians are all about is measuring the amount of circle, so the degrees within the circle, with respect to the circumference of that circle. So if you have 2 pi, you're talking about a full revolution, because that's the full circumference, whereas if you had pi, we're talking about half a revolution, in which case you have half of the circumference. Converting between radians and degrees is a simple calculation. 2 pi in radians is the same as 360 in degrees, and so all you have to do is rearrange to get one of those on its own to get the conversion formula. The way I've always remembered this is you want to multiply by pi if you want to go into radians, because you want to put pi into your expression, and you'll be dividing by degrees, so dividing by 180. Whereas if you're going into degrees, then you want to divide by pi. You want to cancel the radians. That's just a bit of a silly whatever, but that's how I always memorized which way goes which. So if you want to convert 3 pi over 4 to degrees, nice and simple, you're just going to multiply by 180 and divide by pi, since you're converting to degrees. Alternatively, converting 270 degrees to radians, well, you're going to multiply by pi and divide by 180, because you are converting to radians. Okay, trig ratios. So this is the SOHCAHTOA stuff, where you have sine is opposite over hypotenuse, cos is adjacent over hypotenuse, and tan is opposite over adjacent. And so the SOHCAHTOA acronym helps you with that, because the first letter of each of those sections of SOHCAHTOA tells you what trig ratio is being discussed. S for sine, C for cos, T for tan. Then the next two letters tell you what the ratio is going to be. OH means opposite over hypotenuse. AH, adjacent over hypotenuse. OA, opposite over adjacent. We can use this to help solve ratios. So we're told to find sine theta in this case. So it's worth understanding what side of the triangle is labeled as what thing. Hypotenuse is always the longest length of your triangle. The adjacent and opposite will depend on where your angle theta is located. If your angle is here, well, I guess it doesn't matter where the angle is, the adjacent is always the side that the angle intersects. So in this case, you can see the angle is intersecting the hypotenuse and this length here. That length is therefore the adjacent. The opposite is always going to be the side that the angle does not intersect. So in this case, obviously that left-hand side. If theta was here, where I've highlighted with the cursor, the adjacent would be here now, and the opposite would be there. Hypotenuse always remains the same, always the longest side. So in this case, sine theta, we want opposite over hypotenuse. We know the hypotenuse is 4, that's the longest length, and we know the opposite, since theta is here, the opposite must be 2. And so 2 over 4, a half. That is going to be sine theta. You can use that to find an unknown side length. Specifically if you have in this case, if you have an angle that's associated with it. So in this case, we have the hypotenuse, we have theta, and we have this adjacent that we're unaware of. Well, if the adjacent is what we care about, then one thing we would want to do is create an equation that has the adjacent in it. You've got two options there. You've got cos and you have tan. The way you pick between each is you look at the other information that you have. Because you have a hypotenuse as well, you'd want to pick cos. If you picked tan, you would be in a situation where you don't have that the opposite, right? So you couldn't do your opposite over adjacent. But in this case, you would have your hypotenuse of 4, your adjacent of x, and your angle of theta, in this case 31 degrees. So all you do is sub all the known values into there and then rearrange for x. In tech free, you just leave it like this. In tech active, you just make sure that your calculator is in degree mode and you just hit Control Enter on that. On Casio, it's down here. And again, it's the same thing. Simplify your answer or just hit this decimal button here. I believe both work. Solving for unknown angles, well, this is where you're doing the inverse trig. So what that means is you look at the length that you have with respect to your angle, and you identify what ratio is best used in this case. So since theta is here, this is the hypotenuse, this is the opposite. So if you want to know what this angle is, you'd want to use sine theta because you have both the opposite and the hypotenuse. Now, we know sine theta is equal to a half in this case, but we don't want sine theta, we just want theta. The way this works is you can get theta on its own by doing the sine inverse of whatever it equals. So instead of putting theta in the brackets, you now say sine inverse and you put the half in the brackets. In tech free, you would leave it like this for now. We'll later have a look at the exact value that this will be. But pre-understanding the exact values of trig, this is where you would leave it. Tech active, you go into, well, there's a couple of possibilities. One is literally just do sine inverse of a half, in which case you'll get pi over 6, which some of you might recognize as an answer. And the other opportunity, or the other possibility rather, is to do a solve on your function. In this case, I've left my calculator in radians because the vast majority of what you do in math methods will be in radians. So it's a good default to have. But in this case, if you're doing the solve approach, you just want to make sure that you limit your domain. In this case, I've done it from 0 to pi over 2. We'll look at why that mattered in a moment. But here it is on the TI Nspire, here it is on the Casio. Same. Okay, trig ratios as functions just means that instead of them just being ratios on their own, we can call them functions. And we can do all sorts of things with that function. We can graph it, we can solve them, just like you would for any other function, like quadratics or polynomials. Okay, that's it for that. Next up, the unit circle. So we talked about what the unit circle was initially. One other thing that's worth identifying from here is that any given coordinate on the unit circle can be given by the cosine of theta or the sine of theta, where the cosine will always be the x and the sine will always be the y. The reason why this works is because if you look at, let's say this point here is p of theta, you can actually create an implied triangle out of this, where you just draw directly down from the point and your hypotenuse is connecting it to the origin. There is some theta that will be involved with that angle, and if you recognize that the hypotenuse is 1 in this case because the radius is 1, then what you find is, well, in this case you have adjacent here because that's the bit that intersects theta, and you have opposite over here because that's the bit that theta is not intersecting. And what you'll find is that this bit here will always be given by cos theta, and this bit here will always be given by sine theta. Cos theta being horizontal means that's an x value, in which case you get the x coordinate. Sine theta being vertical means it's a y value, in which case you have y equals sine theta. The reason why is because since sine theta and cos theta are both divided by a hypotenuse, it follows that when the hypotenuse is 1, the opposite and adjacent will be, well, as you expect. One moment. Something stuck in my throat. Okay. So that's that. This is just a bit about why the gradient is tan theta. So if you look at this this line here, this hypotenuse, that has a slope associated with it, right? Like any other linear line would. The slope of any line, or the gradient of any line, is always given by the rise over run. And so if you think about the rise as being sine theta, since that's how vertical it is, and the run as being cos theta, since that's how horizontal it is, then rise over run, the gradient, should be sine divided by cos. And if you weren't already aware of it, sine divided by cos is tan. And so if sine divided by cos is gradient, then tan must also be gradient. Okay, exact values of the unit circle. So the first thing we'll look at are the quadrant boundaries themselves. I mentioned that 2 pi was a full revolution, and so you can sort of just break that down to figure out what each of the quadrant boundaries would be. So pi would be half, pi over 2 would be a quarter, and then you could fill in that remaining spot as as 3 pi on 2. Each of these, since the circle is a radius of 1, just have either plus or minus 1 as their coordinates, right? Like if you're looking perfectly horizontal to the right, your x value is oh, hang on, that's broken. Whoops, that needs a fix. This should be the coordinate 1, 0. Your x value being 1 all the way to the right, and your y value should be 0. This one is correct. X value is 0 since it's on the y-axis, and the y value is 1, and so on and so forth. The table hopefully has it correct. Let's see. So cos is 1 at 0. Yes, it is. Okay. So you can just forget this little bit here. Here's just a table of what that all looks like instead of having an image, depending on what you prefer. Specifically of interest will be the tan values, because those don't actually appear as coordinates, but rather the ratio of those coordinates. So because tan is sine divided by cos, if you have a look at how that would work, 0 divided by 1 is 0, 1 divided by 0 is undefined, 0 divided by 1 is still 0, 1 divided by 0, again, anything divided by 0, you're going to have undefined. So that's one way you can have a look at knowing the interquadrant angles. Oh, sorry, the quadrant boundaries. The interquadrant angles are the pi over 6, pi over 4, and pi over 3. Those are the ones that you need to memorize, and those will be all contained within quadrant 1 here. All of those. So the maximum there was pi over 3, which is, of course, less than pi over 2 as far as fractions are concerned. Memorizing the corresponding exact values, you can think of as everything is divided by 2. So all those values are divided by 2 for sine and cos. And all you do is go in order 1, root 2, and root 3. For cos, you do the opposite. So it's 1, root 2, root 3, and then you go backwards in that order. One other way that I like to memorize that is to imagine them as x and y values, which they are. So as long as you know the values are half, root 2 over 2, and root 3 over 2, you can kind of get an idea of figure out what should go where. Because the shallowest angle, if you were to draw a vertical line all the way down, that's got the largest x value. It's the furthest away. So if you see pi over 6 would be there, pi over 4 would land here, pi over 3 would land here. This one's the furthest to the right, and so it should get this x coordinate should be the largest possible x coordinate, the root 3 over 2. Correspondingly, it should also get the smallest y value, because again, if now you're looking horizontally, you've got smallest y value, slightly bigger again. So in order ascending, you just look at the relative positions of the x and y, and then that can allow you to position where those x values are without having to think too hard about it. The reason why that becomes important is because you don't have to just do this. You also have to know these ones, and these ones. You need to know the entire thing. But what you'll notice is that there's a lot of repetition. This coordinate and this coordinate are basically the same thing, except this is negative. Same can be said about this, same can be said about this. The reason why is because on the left-hand side of an xy axis, x is negative. You'll notice that in this quadrant, only x is negative and the y is positive. just like you'd expect on the xy axes. Same can be said here. Both of these are positive, xy axes. Both of these are negative. Only y is negative here. But as far as the actual values of the coordinates, you can look horizontally, you can look vertically. These are all the same values, it's just whether or not you put a negative in front of it or not. Okay, that's that. I did brush over the tan values. There's a few things you can do for tan. You can either memorize the tan values of 1 over root 3, 1, and root 3, or, because you already know sine and cos, you could just divide sine by cos to get those values. It does pay off in the end to memorize the tan values, because you do want to be able to recognize what they are. And so one way that I've brought up to memorize tan values is to have a graph like this, have a different unit circle. You won't see this anywhere else because I made this. And so the way this one works is you have all the tan values. You'll notice I've written root 3 over 3 instead of 1 over root 3. Those are the same value, by the way. Just a brief, what do you call it, intermission here. If you have 1 over root 3, this is called rationalizing the denominator. And what you do here is simply multiply the top and bottom of your fraction by whatever the root is. So if you were to do that, you'd have 1 times root 3 over root 3 times root 3. Root 3 becomes on the top, and whenever you have a root times itself, you just get whatever's inside the root. So root 3 over 3. Those two roots are the same value. The reason why I've elected to do that one instead is because it makes it easier to understand where the values go. If you remember that tan is the gradient of the line, then all you have to do is look at the slope of the line and figure out which of the values should get the tan value. The steepest line should get the largest tan value. The shallowest line should get the smallest tan value. You've got root 3, you've got 1, and you've got root 3 over 3. So it's kind of easy to compare them all. Root 3 is definitely bigger than 1, and when you're dividing root 3 by 3, well, that's going to make quite a small number. Because if you estimate what root 3 is, it's somewhere between 1 and 2. 1 squared is 1, 2 squared is 4. If you're aiming for 3, you've obviously got to be somewhere in between those things. And so whatever that is, dividing it by 3, it's going to get you a smaller number than 1. And you can see that any given line has the same tan values because the slope of that line is the same. So if you compare this one, -1, -1, it's the same black line. It's another way of memorizing it. As for the angles, there's a couple of ways you can do it. One way is to simply memorize pi over 3, pi over 4, and pi over 6, and then just count around the unit circle. So you've got pi over 3, 2 pi over 3, 3 pi over 3, because 3 pi over 3 is just pi. And the way you know how many times to count is simply by identifying what pi over 3 means as a portion of your circle. It's usually easiest to think of half circles in this case, because pi is your half circle, and so pi over 3 must be thirds of that. So 1/3, 2/3, 3/3, and I guess if you want to say this is no thirds. And then you just keep that pattern going. So, and you just duplicate that on the bottom. So you got pi over 3, 2, 3, 4, 5, and 6 pi over 3. Same for pi over 4. Pi over 4 means of this entire half circle, you are dividing that into quarters. So there's 1 quarter, there's 2 quarters, there's 3 quarters, 4 quarters. Flip that vertically as well. And pi over 6, same thing. You're dividing this up into sixth. Except that time you'll get a duplicate, because pi over 6, 2 pi over 6 becomes pi over 3. So you'll get a bit of doubling up there. That's one way. The other way we can look at, like at the very end, which is using reflection to help you out. So very, very briefly, the idea is that instead of starting at 0 and counting this way, you say, okay, I know my reference angle is pi over 3, so this version over here should be pi minus pi over 3. and that gets us there. If you don't already know what I'm talking about, we can look at that at the very end. Okay, and negative angles. So the idea of negative angles is simply that instead of going in an anti-clockwise direction, which you can see these all are, so they're increasing as you go anti-clockwise, in this case we're going in a clockwise direction and counting the exact same values. So one way is literally just to calculate in that clockwise direction and then just count. The alternative is to simply, is to simply look at the equivalent positive version and then flip vertically. So if I want to know where negative 2 pi over 3 is, I look at 2 pi over 3 and then I flip vertically. This spot here is negative 2 pi over 3. That's at least my preferred way of doing it. Okay, that's that. Evaluating circular functions. So this is where you are basically using the unit circle to figure out what the exact value is for that particular angle. So one example I have here is evaluating sine of 3 pi over 2. All you do is look up 3 pi over 2 on the unit circle. You will have to memorize this, but for now you can use a lookup table until you get, you can use the lookup here. And you recognize what that coordinate is. In this case, it's 0, negative 1. Once you've identified what the coordinate is, you write the corresponding coordinate value, the x or the y, depending on if you have sine or cos. Recall that sine is the y, cos is the x. So in this case, because you have sine as the y, sine of 3 pi over 2 is therefore going to be negative 1. If you have angles larger than 1 revolution, one way to go about it is to simply just keep counting to get there. This is a pi over 3 angle, and so if you go to your unit circle, you can see pi over 3, 2, 3, 4, 5, 6 pi over 3, and then once more for 7 pi over 3. That's another way of doing it. You just count until you hit that spot. Alternatively, what you could do is just, if you have quite a large value, then my recommendation is to convert that to a mixed fraction. You want to know an integer value of pi, and you want to know a fractional value of pi. So all you're doing is converting to a mixed fraction. In this case, it's 9 pi plus pi over 6. The integer value of pi tells you where to start on the unit circle. If you have an odd value, you start on the left. If you have an even value, you start on the right. That's because if you're looking at the unit circle, 0, well, not really odd or even, pi, odd, 2 pi, even, 3 pi, odd, 4 pi, even. All the odds are on this side, all the evens are on this side. So 9 pi tells you start on the left, plus pi over 6 means go to the pi over 6 spot that's in that quadrant. In this case, because it's cos, you give the x value. So the x value there is going to be negative root 3 over 2, hence that is what our answer will be. Negative angles, again, I've said this before, if you want to know where 7 pi or negative 7 pi over 6 is, you first go to 7 pi over 6 and then you flip vertically. That's going to give you this coordinate. It is sine, so you give the y, which is a half. Okay, that's when you have the angle and you want to find the exact value. Most of the time, you're given the exact value and you have to find the angle instead. This is called solving circular functions, and we follow a process like this. Let's try it with an example. So, in this case, we're solving for where cos is equal to root 2 over 2. Specifically, what you'll find is that these questions come with a given domain. This one is from 0 to 2 pi. The first thing you want to do in these questions is make sure that you have an exact value expression. All that means is that you have a circular function on one side and an exact value on the other side. We already have that. Next step, we won't have to worry about for a little while, so we'll ignore that for now. Next step after that, find every solution within our given domain. So what you want to do is pull up your unit circle and look for all the spots where cos is equal to root 2 over 2. That's here and here. All you do from there is give the angles. That's it. So if your domain is from 0 to 2 pi, that's 1 full revolution, so you want to give everything within 1 full revolution. Sometimes it requires a bit of rearranging. This is not an exact value expression yet, but if you add root 3 and you divide by 2, you get the expression you're looking for. Again, this is from 0 to 2 pi, so you just find where is sine equal to root 3 over 2, which is here, and you give those angles. If you have a different domain, one possibility is that you're going in a negative direction. What you're going to do is go as far forward as you can and as far back as you can. Usually you want to go 1 full revolution forward and then work your way back. In this case, we're doing negative pi to pi. We want to know where is sine equal to 0. Well, sine is equal to 0 here and here. So if you're going anti-clockwise, you have 0 and you have pi. Those are your angles up until the upper bound of pi. The negative direction would be 0 and then going this way to hit negative pi. So the 3 solutions that you have in this case are 0 and plus minus pi. So again, you just want to make sure that you're doing everything within that given domain. Okay, nasty one. If you have anything inside the brackets other than just x, under these circumstances, what you want to do is, well, firstly, make sure you have an exact value expression, which means circular function on one side, exact value on the other. When you have this situation, you want to simplify what you're looking at here. My recommendation is take everything that's in the brackets and replace it with a single letter. I'm going to use U. When you do that, you have to fix up this domain. So what you want to do is convert it from an X domain into a U domain. And the way you do that is you take the lower bound of the X, sub it into your U equation, and that becomes the new lower bound of your U domain. So I'm taking the 0 from here, subbing it into this, which looks like that. That becomes pi over 2. Same thing for 2 pi. Hence, my new circular function equation looks like this. Not so bad now. Cos equals a half at these spots on the unit circle. But what we find is that our domain is a bit special here. So we can't just go from 0 to 2 pi this time. We now have to fix our answer up a little bit. Already we can see that since pi over 2 is our lower bound, this pi over 3 spot shouldn't really belong. We'll worry about that later. For now, what we're going to do is max out this domain. The way that works is you simply take these solutions that you found and repeatedly add 2 pi to them to get the next solution on the next revolution. The reason why that works is because 2 pi is a full revolution. So if you start here, pi over 3, and add 2 pi, that's the same thing as doing a full revolution starting from 2 pi. You do that for all of your answers, and you keep doing that until you exceed the domain. So adding 2 pi here, adding another 2 pi here, and in this case we have our full list of values where we have exceeded the domain, both in the lower bound and in the upper bound. From there, you trim. We said before, pi over 3 is too small, and 17 pi over 3, as we've just found now, is going to be too big, and so we're going to kill those from the list. If you ever need help comparing fractions, just convert them to the same denominator. So you want to compare 17 pi over 3 to 9 pi over 2, just cross multiply them. They'll now have the same denominator, and you can very quickly see which is bigger than the other. But okay, that doesn't belong, that doesn't belong. Here are our solutions. From there, we don't want U solutions, we want X solutions. So all we do from here is replace what U was in its X form. So instead of saying U equals all this, we say X, or at least the 2 bracket X plus pi over 4 equals all that. All you do from here is get the X on its own. That means divide everything by 2 and then subtract pi over 4 from everything. Looks like a lot of work. It is a lot of work. This is probably one of the more complicated ones you'd come across, but that's the game. At the end, you'll see that all the solutions that we have are now between 0 and 2 pi. So normally you think of 0 and 2 pi as one revolution of the unit circle. In this case, we ended up with 2. So, well, I guess even more than 2, technically, since we killed the first solution. So we did roughly 3 revolutions, give or take. This domain is deceiving. So my recommendation is do this method so you fix the domain, and then it becomes a bit more obvious how it happens. Because 0 to 2 pi, as I said, usually you think 1 revolution. Not the case. Okay. These are just getting more and more complicated. Sometimes you'll have to use other solutions like null factor law, which requires factorization. So you can take a common factor of cosine out of the left-hand side. Null factor law says that either cos x equals 0 or cos x plus 1 equals 0. And so what you end up doing is just solving both of those individually using the techniques I've outlined earlier. Some solutions will have, or some equations rather, will both have a sine and a cos in the equation. The way you typically handle this is converting to tan. So what that means is you try to get it to a situation where you are able to divide both sides of your equation by the sine term. I've chosen to rearrange beforehand. You could just go off rip and do it anyway. But the idea is that when you get to a certain stage, you divide. Oh, I divided by cos, sorry. Sorry, other way around, because it's sine divided by cos. So you want to divide by the cos. Dividing both sides by cos will cancel the right-hand side out and turn this into tan. Once you have just a single circular function, it becomes a bit more obvious how you would handle that. You solve it like any other circular function. Where does tan equal -1 over root 3? Well, we used the methods I've outlined earlier. Okay, general solution is, well, there's a bit to talk about actually. Not a whole lot different to the solving circular function stuff. The general solution is here because when we're solving circular functions, the solutions repeat basically forever. You notice that you could go forward forever or backwards forever as far as the unit circle is concerned. The general solution just says, nah, don't want to deal with that. Just give me a solution that tells me every possible solution to our circular function. Pretty much all you're doing is sliding in this plus 2 pi n term into your solution, and that's fundamentally all it's changing. So we can see what that looks like. If you want to solve for where sine x equals -√3 over 2, well, for one, you'll notice there's no domain. That's your indicator that a general solution is required. But usually it'll tell you, find a general solution anyway. Okay, steps 1 and 2, not necessary right now. What you do here is you find every solution to this within 1 revolution. So sine is equal to -√3 over 2 on those spots. Cool. It's at this stage that you add your 2 pi n after you've found those spots. So you go from having the 4 pi over 3 and the 5 pi over 3 to now having both of those adding a 2 pi n to them. That n term basically just stands for the number of revolutions that you go around the unit circle. So n equals 3 would mean 3 forward revolutions, and you can also pick -n as well, which is a little bit different. Oh, sorry, n equals 3 will be 4 forward revolutions actually, because you got this initial one. Anyway, point being, it's basically a stand-in for the revolution number. In this case, that's literally it, because there was nothing else special that was required. The only thing I will touch on about that is what happens if you have a more complicated situation where you have like a 3x in there. This is where the order in which you do things matters a lot. So as before, you do your substitution. In this case, we're looking for where sine is equal to -√3 over 2. That's going to be these spots here. You add the 2 pi n immediately after finding these spots. The reason why is because when you rearrange to get x back on its own, these terms need to be divided. Everyone stuffs this up. Don't be that person. Put the 2 pi n as soon as you find the solutions, then divide by 3 at the end. Okay, that's what I wanted to touch on there. There is a bit more nuances as to how you can solve cos and tan. We'll probably get to that. Yeah, no, we could look at it actually. Okay, so for sine, you're going to always have basically a split answer. You're going to have x equals one thing plus 2 pi n, and x equals another thing plus 2 pi n. This will not necessarily be the case for cos and tan, depending on how far you simplify your solution. Okay, in this case, cos is equal to negative root 3 over 2. Do the exact same steps. Here's where it equals it. Add 2 pi n to them, and you could call that a day if you wanted to. But one thing to notice about cos is that the cos solutions are always vertical to each other. What that means is it's an equal distance away in the positive direction as it is in the negative direction. And so one alternative way of saying this is to say, well, instead of calling that spot 7 pi over 6, we could call it negative 5 pi over 6, since those are the same value. You have a positive 5 pi over 6, you have a negative 5 pi over 6. You could condense that down into a plus minus 5 pi over 6. That's pretty much it. So if you're aiming for the top marks, this is what you give. Otherwise, this will do enough to get you the mark. Tan has a similar thing. So again, where does tan equal root 3? However you want to do that, you could use a tan unit circle, or you could just know where it is based on sine divided by cos. Either way, it's going to be these spots here. The thing to recognize with tan is that it will always repeat every pi instead of every 2 pi. So you'll notice that anytime you find a tan solution, they will always be 180 degrees separated from each other. This means that instead of saying pi over 3 plus 2 pi n and 4 pi over 3 plus 2 pi n, you could kill one of the solutions, usually the bigger one, and then just say pi n for here. So instead of, like, for example, starting here and then doing a full revolution to get back here, and then starting here, doing a full revolution to get back here, you can just say, how about I just start here and do half revolutions to keep hitting these same spots. That's all that's being said here. So instead of doing that, we've killed the 4 pi over 3 spot and knocked off the 2 here to give us x equals pi over 3 plus pi n. That's general solutions. Inequalities. Yeah, why not? Okay, so solving the inequalities is only a little bit different to solving the equations. You still want to get it to an exact value expression where you've basically got it equaling some exact value. In this case, you've got cos is greater than or equal to 0. You still want to do your substitution, all that sort of stuff, right? Sub in u, convert your domain, as we talked about earlier. The next bit that's a bit trickier is finding the domain for which the inequality is true. So this is where cos is greater than or equal to 0. Really, that just means, where are all my x values positive? Well, that's this side. All the x values are going to be positive on the right-hand side of your unit circle. So that's what you give as a domain. As far as angles are concerned, that would mean 0 to pi over 2 for this spot, and then 3 pi over 2 to 2 pi, which is this spot. In this case, we do need to rearrange to get back in terms of x, or in this case t, because we did have a composite function, but fundamentally it's the same idea. You're just going to replace all these u values with their equivalent x values, or in this case, t values. 0 equals pi t over 6, pi over 2 equals pi t over 6, so on and so forth. If you do get a tech active version, then one thing you can literally do is just sketch that circular function and then just look, where is it above y equals 0? Because you're looking for where cos is greater than or equal to 0. Just sketch it and then find those intersections by whatever means necessary, whether you use the CAS analysis tools or whatever. The reason why I specified that is because it usually has trouble solving inequalities. So better off just going straight to the graph, or CAS solving without the inequality. Just where does it equal 0, and then looking from then on. If you have multiple cycles, then you're doing the exact same thing, but then adding the 2 pi to get the next spots. So in this case, where are the y values, because it's sine, Or is that greater than a half? Well, y is positive at the top, and you just draw a horizontal line to cut off anything below the y equals a half. That's going to give you pi over 6 and 5 pi over 6 as your intervals. All you do is add 2 pi to get the next set of intervals. Okay, and then lastly, some symmetries of the unit circle, which I will get into after I have a sip of water. Okay, the first thing is this idea of periodicity. All circular functions are periodic. Sine and cos will have a period of 2 pi, and tan will have a period of pi. This is what we're talking about where circular functions repeat every 2 pi or every pi in the case of tan. So basically put, if I know that sine is equal to 0.43 and I want to know sine of 2 pi plus theta, then all I'm doing is starting from here, doing a revolution, and getting back there. So sine of 2 pi plus theta is also going to be 0.43. So what that looks like as an identity is this. Either sine or cos of 2 pi k plus theta will always be just what it was without the 2 pi k. For tan, again, it's periodic in pi. And so if I want to know pi plus theta, again, it's going to stay 0.29. It's going to shift from being a positive xy to both a negative x and y, but because two negatives divided by each other, sine divided by cos, you're going to have tan as positive in this quadrant. Half period formulas. Here's a nice long list. Wouldn't recommend memorizing them. Instead, better off understanding how to draw these. You can pretty much explain all of these identities that we have a look at with these first quadrant reference angles. So, first one's first. If I know sine theta, what is sine of pi plus theta? Well, we kind of saw what that would look like earlier. The idea of pi plus theta simply means that you start at pi and you add whatever theta is. So if theta is this red reference angle, then starting here and then adding theta must be an equal and opposite angle in that anticlockwise direction. What you'll find is that because these are separated by pi, this is just going to be the third quadrant variant of whatever's up here. So if these were both positive, then these would both be negative. Since we're looking for sine at this spot, we read the y value. The y value over here was 0.72. The y value over here is negative 0.72. Hence, that's our answer. If you have pi minus theta, same idea. But you start at pi, and this time you go backwards by theta. Again, equal and opposite. And the difference is that because you're in quadrant 2, the x value is now negative. So what you find is that for sine, pi minus theta is just whatever it started with in the beginning. This is just the cos variance. If you know the x value here, same thing. Pi plus theta is going to make it negative. Pi minus theta is also going to make it negative because if you're on the left, x is negative. For tan, in this case, because the signs are mismatched, because you've got a sine divided by cos as positive and negative, you're going to maintain negative for tan. So in this case, you have some, it's hard to label the coordinate in this case, but in this case, you're told tan is 0.29. So basically, the ratio of these two terms is 0.29. So when you do your pi minus theta, again, starting at pi minus theta, it just means that you're swapping the x to be negative. So tan's gone from positive in this spot to negative in this spot, so you slap a negative on it. Pi plus theta, since both are negative, tan is still positive in this direction. You can see the overall slope is positive. It's moving upwards to the right, and so tan remains positive. Okay, that's those. Reflection. So, again, these are all true. Let's see why. Reflection literally just means instead of going anti-clockwise, you go clockwise. So what that looks like, again, if you have a reference angle, flipping it this way would mean that the y value becomes negative. So if you're evaluating sine, you've gone from a positive sign to a negative sign. If you're doing cos, you've gone from a positive cos to another same positive cos, because, well, cos is always positive in the right-hand side. Tan, because you've changed the slope from positive to negative, tan is now negative in this spot. So again, you can see all those values here. And then finally, the quarter period formulas, or at least, wait, this is almost finally. So fundamentally what's happening here is instead of doing a full half, you're now doing quarters. And the way that works is when you do pi over 2 minus theta, is you start with your reference angle, pi over 2 minus theta in this case will flip your x and y. So instead of having xy, you now have yx. Whatever was here is now here, whatever was here is now here. So that's going to make a bit more sense when you compare that to the unit circle. A half and root 3 over 2 become root 3 over 2 and a half. They have been flipped. So you've already seen this. For plus theta, it just means that instead of going in this direction, you now go in this direction. So they're still swapping their positions, but because you're now on the left-hand side, this x spot, quote unquote, x spot, is now a negative. That's pretty much it. So for sine, again, start with your value. Pi over 2 minus means you flip the coordinates. Because you want to do sine at that spot, you give the y value, which is not this, but the y value in the y spot. Same for cos, you give the x with your initial reference angle. For plus pi over 2, it just means you swap and make negative. For sine, you give the y. For cos, you give the x. And then the tan ones. So because you've done a flip of the x and y, you've gone from having sine divided by cos to cos divided by sine, which means whatever your fraction is for tan flips. So if tan is 10 over 7, now you're going to have 7 over 10. And because you don't leave the quadrant, you're still going to maintain a positive value. So this is positive, this is more positive. Oddly enough, this one does actually look backwards because technically speaking, you'd want to have this as your bigger angle and this is your small angle. It really doesn't matter. It's just as a guide. You could put the red theta here and the green theta here. Okay, and then plus pi over 2, you'd have this, you flip, and then you make the x negative. Because you've gone from a positive slope to a negative slope, not only do you flip the angle, but you also make it negative. Sorry, not only do you flip the fraction, but you also make the fraction negative. Okay, those are all the flippy angles. The last couple of things would be Pythag identity. So from trig, we know that a squared plus b squared is equal to c squared. Those are just the lengths, right? So c is your hypotenuse, a and b are either your sine or cos. Doesn't really matter which. Because hypotenuse is 1 in a unit circle, you now have sine squared plus cos squared equals 1 squared. Or just that simplified form there. You can use that to solve other circular functions. So if you have sine x equals 3/5, you could use that to solve cos and tan, as long as you know the domain that x could possibly be, your angle. So what you do is you sub the sine value into the Pythag identity, and you rearrange to get cos. It's at this stage where you have a bit of an issue, because you've now got a plus minus value for cos. The way you handle that is with this domain. If you know that x is between pi over 2 and pi, we know we're in quadrant 2. Quadrant 2, x is always negative, cos should be negative. You now have sine and cos. You can find tan by doing sine divided by cos. And that's it.